At the edge of our solar system, one planet stands as a silent sentinel, Neptune. But behind its icy blue storms lies a mysterious history that makes it the final guardian of our cosmic neighborhood. History of Neptune, the last guardian of the solar system. Here we are at the final stop of our extraordinary journey through the most extreme frontiers of the solar system. After exploring Uranus's magnetic anomalies and its upside-down rotation, we're heading toward the ultimate planetary frontier, Neptune, the eighth and most distant of the major planets, a world of titanic storms and profound mysteries that reign supreme in the frigid cosmic periphery. This ice giant doesn't simply represent the final chapter of our exploration, but embodies the triumph of mathematics over chance. The first planet in history discovered not through direct observation, but through theoretical calculations. A world where winds reach supersonic speeds that defy all physical logic, where a great dark spot appears and disappears like an atmospheric phantom, and where a captured moon dances an orbital dance backwards, challenging gravitational conventions. Are you ready for this final, epic journey to the edges of our planetary system? Neptune dominates the most remote regions of the solar system from an average distance of 4.5 billion kilometers, 2.8 billion miles, 30.1 astronomical units, from the Sun. At this incredible distance, sunlight takes more than 4 hours to reach this frozen world, where illumination is 1,000 times weaker than what we experience on Earth. Yet, despite this energy poverty, Neptune turns out to be the most dynamic and meteorologically active planet in the entire outer solar system. With a diameter of 49,528 kilometers, 30,775 miles, Neptune is slightly smaller than Uranus, 50,724 kilometers, but its higher density, 1.64 g/cm superscript 3 versus 1.27, gives it a mass equal to 17.5 times that of Earth compared to Uranus's 14.5. Neptune's orbital period extends for 164.8 Earth years, a time so long that since its discovery in 1846, it has completed barely one complete revolution around the Sun in 2011. Rotation on its own axis takes 16 hours and 6 minutes, slightly faster than Uranus. Unlike its predecessor, Neptune's rotational axis has a normal inclination of 28.3 degrees, similar to Earth's, creating conventional seasons that last over 40 Earth years each. Despite receiving only 1,000th of the solar energy that reaches Earth, Neptune maintains atmospheric temperatures of minus 218 degrees Celsius minus 360 degrees Fahrenheit, paradoxically warmer than those of Uranus despite being farther from the Sun. This thermal paradox is explained by the fact that Neptune radiates 2.6 times more energy than it receives from our star, testifying to an interior still active from geological and thermal standpoints. The story of Neptune's discovery represents one of the most fascinating chapters in modern astronomy, demonstrating the predictive power of mathematics and theoretical physics. It all began with a supposed orbital anomaly. After Uranus's discovery in 1781, astronomers noticed that the planet didn't follow exactly the orbit predicted by Newton's laws. These orbital perturbations suggested the presence of another massive body gravitationally influencing Uranus's movement. In 1843, young English mathematician John Couch Adams, then a student at Cambridge, undertook the ambitious challenge of calculating the unknown planet's position based exclusively on the observed perturbations. His calculations, completed in 1845, identified a specific region of the sky where the mysterious eighth planet should be located. However, the British astronomical establishment showed little interest in Adams's predictions. Meanwhile, in France, astronomer Urbain Le Verrier conducted independent calculations, arriving at similar conclusions. Le Verrier managed to convince German astronomer Johann Galle at the Berlin Observatory to search for the planet in the predicted position. On the evening of September 23, 1846, Galle and his assistant Heinrich d'Arrest pointed their telescope toward the constellation Aquarius and identified an object that didn't appear on the charts, located less than 1 degree from the theoretically calculated position. This discovery sparked an international controversy over scientific priority, with both British and French scientists claiming credit. Today, Adams and Leverrier are recognized as co-discoverers of Neptune, celebrating the triumph of the scientific method and international collaboration. The name Neptune, suggested by Leverrier himself in honor of the Roman god of the seas, was universally accepted. Neptune's atmosphere, relatively thin compared to the planet's size, is composed of 83% molecular hydrogen, 15% helium, 1% methane, and traces of other gases. Methane absorbs red light and reflects blue, giving Neptune its deep blue hue, even more intense than Uranus's, suggesting another unidentified atmospheric component. Despite its distance from the Sun, Neptune hosts the most extreme weather in the solar system. Winds reach speeds of up to 2,100 kilometers per hour, 1,300 miles per hour, the fastest recorded anywhere. These supersonic winds blow in retrograde direction, opposing planetary rotation, a phenomenon still not fully understood. Unlike Earth, where winds come from solar heating, Neptune derives energy mainly from internal heat. Its most famous storm, the Great Dark Spot, was discovered by Voyager 2 in 1989 but disappeared by 1994, replaced by new storms. Such dynamic weather highlights the transient nature of Neptunian storms, with lifespans of just a few years. The planet's magnetic field is also unusual, tilted 47 degrees from its rotation axis and offset from the planet's center. This suggests a non-core origin, possibly from a conductive mantle. Inside, Neptune has a rocky core of silicates, iron, and nickel, surrounded by a massive mantle of hot ices, water, methane, and ammonia, in a supercritical state, behaving like conductive fluids and generating the planet's magnetic field. This mantle makes up most of Neptune's mass and volume, with pressures and temperatures reaching extraordinary levels. Direct exploration of Neptune was achieved only by Voyager 2, which flew by on August 25, 1989, during its grand tour. It came within 4,950 kilometers of Neptune's cloud tops, capturing over 9,000 images and data that revolutionized our understanding of the planet. The flyby revealed the Great Dark Spot, supersonic winds, Triton's geysers, and 6 new moons, transforming Neptune from a point of light to a complex world. NASA and ESA are now developing future missions to Neptune and Uranus as high scientific priorities. Neptune's moons are dominated by Triton, a massive satellite 2,704 kilometers in diameter, holding 99.5% of the mass of Neptune's satellite system. Triton orbits in a retrograde direction, indicating it was likely captured from the Kuiper Belt. It has a cold surface at -235 degrees Celsius -391 degrees Fahrenheit, but shows signs of geological activity, including cantaloupe terrain, icy plains, and tectonic features. Most intriguing are its nitrogen geysers, observed by Voyager 2, which eject gas 8 kilometers high and travel over 150 kilometers, leaving streaks across the surface. Their cause may be seasonal sunlight or internal tidal heating. Triton's thin atmosphere of nitrogen, methane, and carbon monoxide supports clouds and haze and is in equilibrium with the frozen nitrogen on its surface. Other moons pale in comparison. Nereid, the second largest, follows a wildly eccentric orbit, likely due to Triton's capture. Smaller inner moons like Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus orbit among Neptune's rings and are likely remnants of a shattered original satellite system. Proteus is notable as the largest irregularly shaped body not rounded by gravity. Neptune's ring system includes 5 primary rings: Gal, Leverrier, Lassell, Arago, and Adams, named after astronomers tied to Neptune's discovery. These rings are dark, thin, and sparse, with the Adams ring being the most fascinating due to its bright arcs: Liberté, Égalité, Fraternité, and Courage, held in place by resonance with the moon Galatea. The rings reflect just 2 to 3% of light, similar in composition to dark Kuiper Belt objects, and are thought to be young, formed from moon fragments. Hubble and ground-based telescopes have observed the rings changing over time, with arcs appearing or fading, likely due to solar and seasonal influences. Neptune's significance extends beyond our solar system. Ice giants like Neptune represent a dominant class of planets in the galaxy, subneptunes, and super-Earths. Kepler observations show that planets between 1.8 and 4.0 Earth radii are the most common, though our solar system lacks one. Many of these exoplanets orbit close to their stars under extreme conditions. Studying Neptune helps us model these worlds' formation, structure, and atmospheric evolution. Whether Neptune formed via core accretion or disk instability affects our understanding of how widespread similar planets are. Spectroscopy of Neptune-like exoplanets reveals that some retain thick hydrogen-helium atmospheres, while others have lost them, becoming bare rocky cores. Neptune serves as a key to understanding these planetary transformations. As we conclude this journey from Mercury's scorched surface to Neptune's icy realm, we see how each planet adds a unique chapter to the story of our solar system. Neptune, the last guardian of the classical solar system, waits in the deep blue cold, its storms, moons, and mysteries beckoning future explorers to uncover what lies beyond. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.